So in this structure, we not only have a distributed load and a point load that we need to deal with, we'll need to also generate the maximum moment created at A. So I need to draw an influence line for the moment at A. So let's see what that would look like. So I'm going to draw the free body diagram from A to B. Now, since I'm trying to find the moment at A, that's the piece I need. So there's my moment at A. I'll go ahead and put that, I would have a shear at A. At B, I also have a shear. And then there's the matching piece. I just want you to be able to visualize all this. So there's the positive shear at B on that piece. And then over here at C, there's a reaction. You see all the components? Now I left off the axial force here. But there would be axial forces. There would also be here, but we're not going to worry about those. So in the first case we're going to work on, we're going to let our unit load vary somewhere between 0 and 5. So where would the unit load be? It would be somewhere here. And we would locate it from the left side by some distance x. Oh, I did leave off my dimensions. Oh, that's 10. Now looking at the free body to the right, what's the shear at B? What's the reaction at C? Well, there is no load, so nothing's happening. So I can go right to this free body diagram and write an equation for the moment at A. Everybody see that? So I can quickly go in and say sum the moments about A. I have the reaction. Is that positive or negative with my sign convention? Negative. What kind of moment does this create about A? Positive or negative? Negative. So it's 1 times x. So the moment at A equals minus x. Now, why did I not consider the shear at B? Because from the right side free body, we knew the shear at B was 0. Is that okay with everybody? Wow. The confidence is overwhelming. I know what it is. It rained for the first time in 3 months, and you don't know what to do. The sky is falling. You're just really afraid right now. I know. Huh?
It threw me off.
It threw you off?
I went and asked for a rain jacket this morning before I came.
Wow. They haven't issued you one before?
Well, they did, but I was in class today. They did it.
Ah.
I had to get mine.
Is that your official University of Memphis rain gear? Nice. The rest of you need to go over and get yours too. Just walk over there and ask for your rain gear.
Yeah.
It comes with tuition, right? All right, so let's go from 5 to 15. So what changes? Well, my free body diagram on the left side looks the same, except what? This is now over here. So it's not on this free body, is it? It is over here. So now things change a little bit. So now I have this guy here. And believe it or not, it's still a position x from the total distance, right? How do I find, what do I do over here? Well, I need to find how now the position of the unit load affects the shear, and then once I know that, that shear can be passed over here and I can find the moment. So starting with this free body diagram, maybe I'll label this 1 and 2. So starting with free body diagram 2, I want to find my shear at B. I can find that by summing moments at C, and when I do that, I need this distance, which is going to be 15 minus x. So when I sum moments about C, moments about C equal to 0. About C, I get a positive moment from 1 with a moment arm of 15 minus x. And I get a negative moment from the reaction at B times 10. So solve for the reaction at B. It looks like I get 15 minus x divided by 10. That doesn't seem right. Is that right? Let me think about this for a second. Hang on.
Yeah, that's right. 15 plus that. Negative. No, that's right. 15 minus 6 by 10.
Okay.
I mean, you can reduce it down. We have.
No, something's not right. Something is not right. What did I forget? Because when x is right here at 10, I get 5 over, I get a half? Is that what that should be? That doesn't make sense. I did something wrong. Anybody see where I made a mistake? I'm not seeing it right yet.
This one X is at 5.
Sorry, say again?
Shouldn't be where X is at 5.
Thank you. Yes. Now I'm happy. Thank you. You made my day. Thank you, Mr. Reddick. So I was looking at this 10 and I was plugging in 10 here, but I shouldn't. That point is at x equal 5. So you plug in 5 here, now it becomes 1, and I'm much happier about that. Thank you. Okay, so now that I know that, I can come back over to free body diagram 1, and since I know my shear at B, I can sum the moments about A. Let's see what I get. So looking at this free body diagram, the moment at A is negative. The moment at B is also negative, and it has a moment arm of 5. So I just plug this into there and multiply it by 5. So the moment at A should be, let's see, that 5 makes this a 2, right? So I will get negative 15 minus x over 2. Now I got to think about that. I think I like that. Did I do that okay? I think so. So let's plot that. So here's the moment at A. There's the pin, and there's the pin. So for the first 5 feet, I plot that. So that's negative x at 5. That would be a value of minus 5. And I put 5 in here. I get, well, that's screwed up, isn't it? Oops. What did I do wrong? Well, that's right. I can't do anything today. Yeah, that's right. You put 5 in here, you get 10. 10 divided by 2 is minus 5. Yeah. Oh. And now I plot this. When I put in 15, what do I get? I get 0. So I get this. A lot of work for that. Okay? So, what is the maximum negative moment at A for these two loads? So first, if we do the concentrated value, what is the concentrated force? It is 10 kilonewtons. So where do I run my 10 kilonewtons to create the largest moment at A? Right here at B, right? So I have 10 times the ordinate of that axis. So the moment at A for the concentrated load would be 10 kilonewtons times minus 5 meters. I forgot to put the unit on here as meters. So that'll be negative 50. Oops. Negative 50 kilonewton meters. Now what about the uniform load? Well, we just learned that all I have to do is take the area under the curve times the value of the load. So the value of the load in this case is 1.5 kilonewtons per meter. And then I'm going to multiply it by the area under this curve, which is a triangle. So it's 1/2 the base, which is 15 meters, times the height, which is minus 5 meters. You guys are going to have to help me with that. I don't know what this is. Half of 75 is 37.5, and then half again, I don't know, 50-something. Take a shot. 56.25, I'm guessing. Now is the time where we put out a calculator and we... What'd you get? 50.25? 56.25. No way. Really? Amazing. Only on Tuesday. Only on Tuesday. So the total moment, you simply add those two together, which looks like 106.25. That's negative 2. So that's the maximum negative moment at A created by those two loads. Yeah, bless you. So what that looks like is the uniform load applied the whole length of the structure. This would be the uniform load. And that's 1.5 kilonewtons per meter. And then the point load applied at B. So that's the load combination applied to using that diagram to generate those values. Okay? Cool. You guys are well skilled now. That one took about 14